Welcome to the Deep Dive. I want to kick us off today with something Jerzy Neyman, a giant in statistics, once said. He put it like this: whoever has participated in non-trivial research must have encountered the difficulty that none of the statistical procedures found in the books fits exactly the practical situation.
That really hits home, doesn't it? Especially now.
It really does. In our world, just swimming in data, that feels more true than ever. So how do we actually cut through all that noise? How do we get to real cause and effect when, the old tools just don't quite cut it? That's really our mission for this deep dive.
And the solution we're digging into, well, it's this powerful approach called double Debiased Machine Learning, DML for short.
EML, right.
Think of it as a really smart blend. It takes the best of machine learning, its ability to handle complex patterns, and combines it with the rigor of traditional statistics. The goal: to reliably figure out causal effects, even predictive effects, and trust the answers.
Exactly. And for you listening, DML is kind of a shortcut to being properly informed. It helps you get those aha moments, understanding the why behind the data without getting totally bogged down. You end up knowing not just what happened, but why it matters, and crucially, why we can trust that answer.
And the magic, if you like, boils down to two key ingredients we'll unpack: something called Neyman orthogonality and a technique called cross-fitting. We'll see how these work through a couple of really interesting real-world examples.
Oh, yeah.
Yeah, first we'll look at the tricky relationship between gun ownership and homicide rates. And second, the effect of 401k eligibility on people's savings.
Okay, let's unpack this then. What's the basic problem DML is trying to fix? Why do we need something new here?
Well, think about it. You're often dealing with incredibly complex situations, right? You want to know the effect of one specific thing, but there are maybe hundreds, even thousands of other factors, other variables influencing the outcome.
Right, the control variables.
Exactly. And these controls might have really complicated nonlinear relationships with your outcome. Now, traditional methods can struggle with that sheer scale and complexity. And machine learning, it's great at prediction, finding patterns.
But it can overfit, memorize the noise?
Precisely. It can sometimes learn the quirks of your specific data sample too well, which leads to biased estimates of the actual causal effect you care about. DML is designed specifically to get accurate, unbiased answers in these high-dimensional, complex settings, even when using those powerful ML tools.
Okay, so how does it manage that? Let's talk about this Neyman orthogonality. It sounds technical. Is it like a filter?
Yeah, it sounds a bit daunting, but the concept is actually quite elegant.
Yeah.
Think of it like designing an equation, a statistical procedure, in a very specific, clever way.
Okay.
The design makes your main estimate, the effect you're actually interested in, locally insensitive. That means small errors or biases in estimating all those other things, the nuisance parameters we need to account for, but aren't the main focus. Well, those small errors don't really mess up your main result.
So it isolates the main effect from errors elsewhere.
Exactly. Imagine trying to estimate the effect of a drug. You also need to estimate how age, weight, etc. affect the outcome. Those are nuisance parameters. If you use a naive approach, maybe just plugging in a standard machine learning model, any small inaccuracies in how you estimated the effect of age or weight can directly bias your estimate of the drug's effect. It amplifies the errors.
Right.
Neyman orthogonality designs the calculation so that these first-order effects of errors in the nuisance parts just cancel out mathematically. So even if your estimates of the age effect aren't perfectly perfect, your drug effect estimate remains approximately unbiased and reliable. That local insensitivity is the key.
That's a really helpful way to think about it. So DML isn't just about using fancy algorithms. It's about the structure of the calculation, designed to protect the answer you care about from the surrounding complexity and potential estimation errors. Okay, but you mentioned overfitting earlier. How does DML deal with ML models getting too attached to the training data?
Good question. That's where the second key ingredient comes in: cross-fitting. It directly tackles that overfitting problem. You see, complex ML models can be too good at fitting the data they see.
Including the random noise.
Exactly. It's like they memorize it. This creates what's called own observation bias, if you're not careful.
Own observation bias.
Okay.
So cross-fitting is basically a smart form of sample splitting. Instead of using the same data to both train your ML model to estimate those nuisance parts and calculate your final causal effect, you split the data.
Like using one part to learn and another part to test.
Precisely. You might split your data into, say, two halves. You train the ML models for the nuisance functions on fold 1, and then use those trained models to calculate the residuals and the final estimate on fold 2. Then you swap roles. Train on fold 2, estimate on fold 1. You average the results. This ensures the observations used to estimate the effect are different from the observations used to train the models that handle the nuisance parts.
So the model doesn't get to cheat by seeing the answers beforehand. Exactly. It prevents the overfitting in the nuisance estimation from directly biasing the final parameter estimate. In practice, especially with complex ML methods where theoretical tuning is often, well, let's just say tricky, relying on this kind of sample splitting is just much safer. It guards against that overfitting contamination. Now, let's see how this plays out in a common model type. The Partially Linear Regression Model, or PLM, it's a really versatile setup.
Partially linear, so part simple, part complex.
That's exactly it. You assume your main variable of interest, let's call it D, affects the outcome Y in a simple linear way, like a 1-unit increase in D causes a beta unit increase in Y, but you also allow all the other control variables X to influence Y through some potentially very complex, totally nonlinear function.
Okay, so the main effect is simple, but the background context can be super complicated.
Right, and the DML approach to solving this relies heavily on that idea of partialing out or residualizing.
Like cleaning the variables.
Kind of, yeah. Imagine you want the pure effect of D on Y. You need to remove the influence of all those X variables first. So DML uses machine learning to predict Y based only on X and also predicts D based only on X. Then it calculates the residuals, basically, the part of Y that isn't explained by X and the part of D that isn't explained by X.
So you're left with the clean versions of Y and D.
Exactly. You've partialed out the effect of X from both. Then you simply regress the cleaned up Y residual on the cleaned up D residual. That final simple regression gives you your unbiased estimate of the effect of D on Y. The actual algorithm involves those cross-fitting steps we talked about: partitioning data, estimating nuisance functions on different folds, then doing this residual on residual regression.
Got it. That makes intuitive sense. Clean up both sides before looking at the relationship. Let's make this concrete. You mentioned the gun ownership study.
Yes, a really interesting application. Researchers looked at the effect of, well, a proxy for gun ownership on gun homicide rates across 195 large U.S. counties between 1980 and 1999. So a decent amount of data, 3,900 observations total.
Okay, and what was the outcome and the variable of interest?
The outcome Y was the log homicide rate. The variable D, used as a proxy for gun ownership levels, since direct data is hard to get consistently, was the log fraction of suicides committed with a firearm in that county in the previous year.
A proxy, right. And they controlled for other factors.
Oh, yes, a rich set of controls, X. Things like demographic characteristics, economic factors, all specific to the county and year.
So what did the simple picture look like? Just the raw correlation?
If you just looked at the raw association, ignoring all the controls, you saw a positive relationship. The estimate was about 0.3, suggesting, a 1% increase in the gun ownership proxy corresponds to roughly a 0.3% increase in the predicted homicide rate.
But that could be misleading, right? Wealthier counties might have different rates for other reasons.
Exactly. Tons of potential confounding. So they applied DML using 10 different machine learning methods, things like random forests, boosted trees, lasso, neural nets, to handle that complex set of control variables, X.
10 different methods. Why so many?
Well, that's actually one of the strengths here. Different ML methods might be better or worse at capturing the underlying relationships in the nuisance functions. And indeed, they found noticeable differences in how well the methods predicted homicide rates or the gun ownership proxy. Boosted trees and random forests seem to do the best job predictively in this case.
Okay, so what did the DML estimates for the effect look like after controlling for everything?
This is where it gets interesting. The actual point estimates for the effect of the proxy on homicide rates varied quite a bit depending on which ML learner was used for the controls. They ranged from about 0.06 up to 0.46.
Wow, that's a big range.
It is. But if you focus on the methods that had the best predictive performance, like boosted trees, the estimate was smaller, around 0.10, and crucially, the 95% confidence interval around that estimate actually included 0. It went from roughly 0.003 to 0.208.
So what does that mean in plain English?
It means that while the estimate points towards a positive effect, There's enough uncertainty that we can't confidently rule out the possibility that the true effect is zero, or even slightly negative, based purely on this statistical analysis. It suggests mild evidence of a positive effect, but it's not statistically significant at the conventional levels.
That really highlights how important controlling for those confounders is, and how the specific ML tool choice can matter.
Absolutely. And there's another important layer here, the caveat about the proxy variable itself.
Yes, you mentioned attenuation bias.
Right. Using the fraction of suicides with firearms as a proxy for overall gun ownership isn't perfect. If that proxy measure has some noise or doesn't perfectly track true ownership, it can lead to what's called attenuation bias. This generally means the estimated effect size, our beta, might be smaller in magnitude than the true causal effect we're trying to capture. It biases the result towards zero.
So the true effect, if there is one, could potentially be larger than what DML estimated here.
Yeah.
Simply because of the limitation of the proxy measure.
That's the concern, yes. DML helps deal with observed confounders, but measurement error in the variable itself is a separate challenge.
Okay, let's switch gears to the business example. Price elasticity for toy cars. What was the setup there?
Right. This revisits an analysis looking at how changing the log price of a toy car affects its log reciprocal sales rank, basically how price affects sales performance.
And previous attempts had trouble finding a clear effect.
Yeah, earlier analyses using simpler methods like OLS with different sets of features often produced confidence intervals that included zero. Even a more sophisticated technique, double lasso, gave a negative interval, but it wasn't super strong.
So what happened when they brought in DML with more flexible methods?
When they applied DML using things like decision trees, boosted trees, random forests, and neural networks methods that can capture complex nonlinear relationships in the controls, the results became much clearer and stronger.
How so?
All the confidence intervals from these flexible DML methods clearly indicated a substantial negative effect. And interestingly, the point estimates were generally more negative than what the simpler methods found.
More negative. Why would that be?
Well, think about confounders. Maybe popular toys, high sales rank, are also priced higher by retailers. Or maybe marketing campaigns boost sales and allow for higher prices. These kinds of things, if not properly controlled for, would tend to make the observed price-sales relationship look less negative or even positive. By using flexible ML within DML to better control for all these other complex factors, the analysis likely stripped away more of that confounding influence, revealing a stronger underlying negative causal effect of price on sales rank.
That makes sense. Better controls reveal a clearer picture.
Exactly. And the fact that these flexible methods also achieved higher R-squared values when predicting price and sales rank supports the idea that they were doing a better job capturing those complex background relationships.
And wasn't there something about nonlinearity in that study too?
Yes, that was another cool finding. They explored transforming the price variable to look for nonlinear effects. The results suggested the relationship wasn't just a straight line. It seemed to be more like flat at first, then decreasing more steeply as the transformed price increased. It showed DML isn't limited to simple linear effects. It can help uncover these more nuanced, nonlinear patterns too. Okay, so we've seen DML with the partially linear model. But it can handle even more complex situations, right? Like the Interactive Regression Model, or IRM.
Interactive, meaning the effect itself changes depending on other factors.
Precisely. The IRM is more general. It allows for fully heterogeneous treatment effects. Imagine the effect of a job training program isn't the same for everyone. Maybe it helps younger workers more than older workers. And it often deals with a binary treatment. You either got the program, D1, or you didn't, DO. The key challenge is that the treatment variable D isn't just simply added on. Its effect can interact with the control variables X in complex ways.
So you can't just separate them easily like in the PLM.
Right. And in this setup, often the goal is to estimate the average treatment effect, the ATE, or sometimes called the average predictive effect, APE. Basically, what's the average impact across the whole population of switching the treatment from 0 to 1?
And how does DML handle this extra complexity? Does Neyman orthogonality still help?
It's absolutely crucial here. In these interactive models, simpler approaches often break down. Just doing regression adjustment or just using propensity scores, common techniques in causal inference, turns out not to be Neyman orthogonal in this setting when used alone with complex ML. They become sensitive to those nuisance estimation errors again.
So the standard tools aren't robust enough here.
Not when combined directly with flexible ML in this interactive setting, but DML uses a specific mathematical structure, a doubly robust representation of the AE, which is Neyman orthogonal. This specific formulation allows you to plug in those high-quality ML estimators for the complex parts while still maintaining statistical validity and getting reliable estimates of the average effect. It's designed for this very challenge.
Let's ground this in the other case study you mentioned. 401k plans and financial assets.
Yes, a classic question in economics. What's the real impact of being eligible for a 401k plan on how much net financial assets someone accumulates? The data came from the 1991 survey of income and program participation.
So outcome is financial assets, treatment is 401k, eligibility, yes, no, and controls are things like
Age, income, education, marital status, family size, things like that. Standard demographic and economic controls.
And the big challenge here is selection bias, right? People aren't randomly assigned 401k eligibility.
Exactly. People who earn more might be more likely to work at firms that offer 401ks, and they might also save more anyway. So just comparing people with and without eligibility could be really misleading.
So how did researchers originally try to tackle this?
The argument in earlier work was that conditional on observing things like income, education, age, etc., factors that influence job choice, you could maybe treat eligibility as if it were randomly assigned or exogenous. The idea was that once you account for why people are in certain jobs, the eligibility itself might be considered almost random within those groups.
That sounds like a strong assumption. What if there are things you don't observe?
And that is precisely the sobering note, as the source material puts it. This is where the causal interpretation gets really tricky.
How so?
Well, imagine there are unobserved firm characteristics. Maybe some firms have a really strong savings culture that encourages employees to save and makes them more likely to offer generous 401ks. If you can't measure that savings culture, just controlling for income isn't enough. That unobserved factor is confounding the relationship.
Or maybe individual traits.
Right. Think about latent confounders, like someone's inherent patience or risk aversion. A very patient person might be more likely to choose a stable job with good benefits, like a 401k, and they might naturally save more regardless of the 401k. Again, if you can't measure patience directly, you have a hidden confounder.
And you can't just look at the data and know if these hidden confounders exist.
No, you can't. The presence or absence of these unobservables isn't something you can typically test for statistically, just using the observational data you have. Arguing for a truly causal interpretation requires deep institutional knowledge, strong theoretical arguments, or maybe specific research designs to rule out these hidden factors. Otherwise, your estimate might just be a predictive effect telling you that eligibility is associated with higher assets after controls, but not necessarily that it causes the entire difference.
Okay, so bearing that significant caveat in mind, what did DML find when applied to the 401k data?
Well, first, the simple comparison without any controls showed a huge difference. Eligible people had, on average, about $19,559 more in net financial assets.
Wow, okay, and with DML controls.
When they applied DML using flexible methods to control for income, age, education, etc., that estimated effect was substantially attenuated. It dropped quite a bit.
How much?
The estimates landed in the range of about $7,800 to $9,400, depending on the specific ML method and whether they use the PLM or the more complex IRM framework.
So controlling for observable factors cut the estimated effect by more than half.
Yes. But what was also interesting and somewhat reassuring was that the results from the different sophisticated DML methods were pretty consistent with each other. And perhaps more surprisingly, they weren't wildly different from what original, simpler econometric methods had found when using the same basic controls.
So in this case, maybe those basic controls were already doing a pretty good job.
It seems that way, yes. It suggests that for this particular question and data set, controlling for the key observables, like income and age, captured a large part of the selection bias. DML confirmed this and provided robust estimates, but it also served to highlight just how crucial the underlying assumptions about unobserved factors are if you want to make a strong causal claim.
Okay, this has been a fantastic tour through the mechanics and applications. Let's try to distill this for everyone listening. We've seen DML in action with different models, different problems.
Yeah.
What are the absolute core takeaway ingredients that make it work?
Right. If you boil it down, the generic DML recipe really has three essential parts. First, you need that Neyman orthogonal score function.
The clever math that makes it robust to errors.
Exactly. That mathematical structure that ensures your main estimate isn't overly sensitive to imperfections in estimating all those nuisance background pieces. It kills off that first-order bias. That's the theoretical backbone. Second, you need high-quality machine learning estimators. DML is built to leverage the power of modern ML. Things like random forests, boosted trees, neural networks, lasso, whatever works best for capturing those complex nuisance functions in your specific data. The better your ML tools approximate those functions, the better DML performs.
So it embraces ML, doesn't shy away from it.
Absolutely. And the third crucial piece is sample splitting, usually implemented as cross-fitting.
The practical step to avoid overfitting bias.
Precisely. Separating the data used for training the ML nuisance models from the data used for the final estimation of your parameter of interest. It's the safeguard against the ML models memorizing noise and contaminating your result.
So putting it all together, Neyman orthogonality for theoretical robustness, flexible ML for handling complexity, and cross-fitting for practical reliability.
You've got it. Those three ingredients make DML more than just another technique. It's really, as the source calls it, a practical meta-recipe. It's a framework that thoughtfully combines insights from classical statistics and econometrics with the power of modern machine learning.
Making it ready for real-world use, getting reliable answers from complex data where older methods might struggle.
Exactly. Ready for rigorous statistical inference on both predictive and causal effects.
So we really journeyed through the world of double machine learning today. We started with the core ideas that clever Neyman orthogonality and the practical cross-fitting, and saw how they apply in different models, looking at everything from gun ownership and homicides to 401ks and savings.
And I think this deep dive really underscores a crucial point. In today's data-rich environment, just having more data isn't the answer. You need the right tools to cut through the complexity, to ask the right questions, and importantly, to get reliable, meaningful insights. DML is one powerful example of such a tool, helping us move beyond just seeing correlations to trying to understand what's actually driving the outcomes.
So, for you listening, what's the takeaway? When you encounter studies or claims based on data maybe about a new policy's impact, a market trend, even something influencing personal choices, it's worth thinking about the methods used. DML reminds us that the reliability of an insight often hinges not just on the data, but on the statistical rigor and cleverness applied. It pushes us to ask, are we truly isolating a cause? Or are we just seeing a correlation, maybe missing crucial confounding factors? Are we looking at the whole picture? Or just the tip of the iceberg?
And maybe here's a final thought to leave you with. If tools like DML give us more confidence in pinpointing specific causal effects within these really complex social or economic systems, how might that change things? Could it shift policymaking or business strategy away from, say, educated guesses towards more genuinely evidence-based interventions? But at the same time, remembering those unobserved confounders we discussed, what hidden factors might still be influencing the outcomes we see, constantly reminding us to stay critical and keep exploring.